Welcome to Power Electronics lecture series. In this session, I'll be going to explain power MOSFET. And to understand power MOSFET, these are my session outlines where I will explain basics of power MOSFET, what are the features which is there with power MOSFET. We'll see there are basically two types of power MOSFET, N type and P type. So we'll see that with symbol. Then we'll see structure of power MOSFET, and then I'll explain how it works, and then we'll observe VI characteristic of MOSFET. So let us begin this with first point, that is basics of power MOSFET. So full form of MOSFET, that is metal oxide semiconductor field effect transistor. So that I'll explain like how it is metal oxide field effect transistor, and that we can understand by its structure. Power MOSFET is having very high switching frequency, and that is about 100 kilohertz. So we can utilize power MOSFET up to 100 kilohertz. That is very good in terms of power electronics, and it is having advantage over BJT, and that is BJT is current control device. So collector current is depending on base current, and even base current is highly depending on junction temperature. So ultimately that is what affecting output current, but that is not there with MOSFET. So BJT is current control device. Collector current increases with the increase in base current, and even base current is highly depending on junction temperature. So if junction temperature changes, there will be higher amount of base current, and that will result into false functioning of BJT. But this problem is not associated with power MOSFET. When we talk about features of power MOSFET, so it is having low input current, it is a voltage control device, it has high switching speed, they do not have problem like second breakdown, it has very high input impedance, and it is an active device. So these are the basic features which is there with power MOSFET. Now let us move on to its basic point, which is symbol of power MOSFET. So when we talk about symbol of power MOSFET, it is a 3-terminal device. This is gate, this is drain, and this is source. And here this symbol, that is for N channel. And for P channel, this is drain, is gate, and arrow that will be in outward direction. This is P channel MOSFET. So ultimately MOSFET is 3-terminal device, gate, drain and source. N channel and P channel, there are two types. Now let us try to understand what will be the structure of power MOSFET. So in power MOSFET, source is attached with N plus layer. N plus means highly doped N type material, and drain is attached with N plus layer, and N plus is attached with N minus layer, and this is even referred as drift layer. This is even referred as drift layer, and in between there is P type layer, that is even referred as body. And little simplified diagram of power MOSFET that one can see over here, where here drain and source, that is directly connected to N type material, and gate is connected to SiO2 layer. So this is what creating capacitance. One can see here gate is connected and it is not directly connected to p-type layer. It is connected with SiO2 layer that is very thin. Thickness of SiO2 layer that is around 1000 angstrom. So thickness of SiO2 layer that is around 1000 angstrom, and this is what creating a capacitance. So gate is connected via SiO2 layer, drain and source directly connected to n-type layer, and this is a structure of n channel MOSFET. Both are same, only the difference is n minus layer, that is what we are connecting in power MOSFET. This is even a MOSFET, but in power MOSFET n minus layer, that is what drift layer, which will improve switching speed as well as it will improve voltage handling capacity. So because of drift layer, switching will improve as well as voltage handling capacity that will get improved. And this is simplified diagram of power MOSFET, where there is actually n plus layer, and at the side of drain there is n minus layer, drift layer. Now let us try to understand working of power MOSFET. Now to understand working of power MOSFET, usually we are deal with to connect gate to body, where gate is connected with positive terminal of battery. Let us say this is positive, this is negative, VGS. So gate is connected with positive terminal and body is connected with negative terminal. Now as we connect gate to positive terminal, this SiO2 layer, this is SiO2 layer, and that will act as a capacitor. So as we are connecting positive terminal of battery to gate, it will be acting like capacitor. So there will be positive charge carriers which is generated on this plate, and on other side of this there will be a generation of negative charge in p-type layer. So as we increase this VGS, this negative charge will increase. Now if I further increase VGS, it will increase this negative charge. So ultimately it is creating this channel. It is creating this channel. So this is what induced channel and even inversion layer. See, this negative charge induced because of this capacitor by this SiO2 layer, that is called as induced channel in p-type layer, and even that is referred as inversion layer. So ultimately as channel is created over here, if drain is if I connect drain to source by drain is connected with positive terminal of battery and source is connected with negative terminal of battery, so VDS. So in that case now there is what channel created, so ultimately it will result into flow of current. So this is what ID, that will happen like this. If this channel is not there, then there will be a depletion region in between, and that depletion region will not allow flow of current to pass through it. But as we increase VGS, there will be increase of ID current. So that is how power MOSFET is functioning. So power MOSFET, that is controlled by this VGS voltage. So power MOSFET is controlled by gate voltage. That's why MOSFET is voltage controlled device. As we increase VGS, it will be inducing more amount of negative charge carriers in p-type layer at this side, and that is what inducing n-type of channel in this, which will allow flow of current passing through. So ultimately, as we increase VGS, ID current will increase, and this induced channel is even referred as inversion layer. Now here let us try to understand what will be the characteristic of power MOSFET. So first I'll be explaining characteristic which is transfer characteristic, that is VGS versus ID characteristic. VGS is input voltage and ID, that is output current. So ultimately we can say this is what transfer characteristic. So in transfer characteristic, what will happen is, as we increase VGS, current ID will increase. So initially, if VGS is something, initially current will not flow, but after some value, as we increase VGS, current will increase. And this is what happening at constant output voltage, and output voltage is VDS. So at constant output voltage, as we increase VGS, ID current will increase like this, and this is what transfer characteristic. Now let us try to understand one another characteristic. So here this characteristic is there in between VDS and ID. So VDS is output voltage and ID, that is output current. So ultimately this is a characteristic at output side. So we can say this is output characteristics. Now in this characteristic, we will be keeping input voltage constant. So here we will be keeping input voltage constant. Now at constant input voltage VGS, if we increase VDS, initially ID will increase, and then after ID will get constant, and after a breakdown there will be high amount of flow of current of ID. So this is what happening at constant VGS. Now if I further increase VGS, let us say this is what VGS, that is 0.5 voltage. So that at that time, this is how current is increasing. Initially it is increasing, and then after it will get constant, and once breakdown is happening, high amount of current is flowing. Now if I increase VGS further, then characteristic will be similar, but now at higher amount of ID. So initially as we increase VDS, ID current will increase, then after it will get constant, and once it is getting breakdown, there will be high amount of flow of current. And this is what the case which is happening at 1 voltage. Now further if I increase VGS, initially as we increase VDS, output current will increase, but now level will be little more. Then after it will get constant, and then after breakdown there will be high amount of current flow, and this is what VGS is equals to, let us say, 2 voltage. So ultimately if we see this region where nothing is getting conducted, so that is cutoff region. Over here, as we increase voltage, current is increasing. So ultimately we can say this is ohmic region. In this region, voltage and current both are, current is constant with respect to increase in voltage, and this is what? Active region. And here there is a breakdown, so one can say this region is saturation region. So this is what output characteristic of power MOSFET. Thank you so much for watching this video. If you have any query regarding power MOSFET, you can place that in comment so that we can have a discussion, and I will try to sort out those queries. And even if you have any suggested video, just write down in comment so that I can make out video based on that topic. Thank you so much for watching this video.